Okay, today let's look at the we call nonlinear beam. Actually, why it's called nonlinear? Because we use a nonlinear relationship between the strength and displacement. Okay, so and the main feature is we allow neutral axis to be stretched. Okay, the actual neutral axis can be stretched. That will become a beam, have an actual loading. So, for example, if you use a cable or tendon, something, okay. If this is compression, it will become a beam column. And today we just show if it's under tension, okay? But we derive this equation, okay? Now for a beam with the element dx, okay? And we look at the center point. We have a vertical downward coordinate z and x coordinate, right? And this point during the motion will have become to the element to here, okay? With horizontal displacement, we say u, okay? And vertical displacement w, the center point, okay? And this element rotate angle is dw dx, okay? Because this is a dx, this is dw, right? So the slope will be dw dx, yeah. And okay, so for any point, original at with a z bar coordinate, this point will move to here, right, to here. So the distance here, this horizontal distance will be, we call u bar, is equal to okay, u bar is here. Because this point moved to here. So this is u bar. And u bar is equal to u minus z bar dw dx. Because this rotate, right? So this small displacement is z bar times partial dw dx, right? But it's toward the left side, so we put a negative. Okay, so this distance is from this point. Now I enlarge it. This point we have a u. So this point we have u bar. So u bar equal to u subtract z bar dw dx. Okay, let's enlarge it from this dx element. Understand? Because deformation, rotation. So this point, for example, this is point, say point A, move to A from. Okay, the whole being downward rotate. Okay, so A point to A point. So the horizontal displacement for this A point, point A, it moved to this A prime. Okay? Yeah. So my kinematics, yeah, that's most important in beam theory. We use the geometry and the kinematics, the U bar is equal to U minus Z dW dx. Okay? And let's recall the nonlinear strain displacement relation. We have epsilon ij is half U bar I j plus U bar ji plus U bar ki times U bar k j. In linear theory, we just consider this. But for nonlinear, we have added a high order term. Okay? So that means epsilon x is equal to half partial U bar, okay? U bar, okay, in here, U bar x, okay? And the partial x1 x plus U bar x plus xx, right? U bar x plus partial U bar 1 U bar x partial x times partial U bar x partial x plus U bar y plus x partial U bar y partial x plus partial U bar y z partial x. Okay, the U bar x here is equal to the U bar there. Okay, partial U bar z partial x. So this is for actual strength. We have this relation, right? Or we say that U bar x equal to U bar, sorry. And the U bar y is equal to, we call say V bar, okay? And U bar z equal to W bar, okay? W bar. And all are function of x. Okay, yeah. All right. So that means for each point in the space, we have this 3D. Okay, so this is x, this is y, and z, and we call this U bar, and this we call V bar. It's called W bar. Okay, W bar. So from this relationship, we can say epsilon x is equal partial U bar, partial x plus half partial W bar, partial x squared. And yeah. Okay, and half partial U bar partial x squared plus half partial v bar partial x squared, right? And epsilon y equal to partial v bar partial y plus half partial w bar partial y squared plus half partial u bar partial y squared plus half partial v bar partial x squared. Okay, and epsilon z, the vertical strand, is a partial w bar partial z plus half partial w bar partial z squared plus partial u bar partial z squared plus half partial v bar partial z. So this is y. Okay. Square. Okay. Now, right. So for plane problem, the v bar 0, right? Okay, so all this term we have to drop. This is 0, right? And this is 0, right? But for anyway, we have epsilon x is what we consider. But if you need to consider epsilon y after you got a u w bar, maybe and the w bar. Okay, here w bar is a function of, okay, u bar is function of x and z. Okay, and others are function of x. All right. So any term with respect to z, this is okay. We keep it. Okay, and the u bar nothing to do with y, so this term drop, right? And w bar nothing to do with y, so 0. So this equation, epsilon y is equal to 0, and epsilon x will be, okay, this term, okay, right, will be partial u bar partial x plus half partial u bar partial x higher order term plus half partial w bar partial x squared. Okay, here we use partial because we have two variables, but for w you can use a total differentiation, doesn't matter. But epsilon y 0 and w bar nothing to do with z, so this is 0 and this is 0, okay, and this is 0 and 0, so epsilon z equal to 0. So from this assumption we have this strain field. My strain field depends on the actual strain displacement, vertical displacement, and the epsilon y and epsilon z are 0. So for this being, we have actual strain due to actual displacement and band diffraction. Okay, so that's my strain relationship due to this nonlinear strain and displacement relations. Yeah. Okay. Yeah. Okay, and for here, we further assume this, if this is also high order term. So we dropped it, it's high order term. If u bar is smaller than 1, okay, or partial s smaller than 1. So high order term compared with this, so drop it. So for the strain, epsilon x, we only have epsilon x is equal to partial u bar partial x plus half. Because the w may be much, much bigger, okay? So we keep this partial w bar partial x squared. So this is my strength displacement relationship in nonlinear relationship. Okay. All right, and you put the u bar here. The u bar, we have the relationship here. Okay. So back to our beam theory. So let me go back here. So back to our beam theory. We have u bar equal to u minus z bar, right? Okay, okay, z will be fine, right? Z, okay, z. We forget z x bar, z, and the d partial w partial x is our relationship. Okay, so now, so epsilon x will equal to the and w bar equal to w. Okay, in series, w bar all the same. Okay. Okay. So epsilon x will become partial u, partial x, that will be partial x u minus z, partial w, partial x, right? And plus half partial w, partial x square. All right. So this is equal to partial u, partial x plus half partial w, partial x squared, and minus z, partial w, partial x squared. Okay, this is a second derivative, and this is a. We define this is a epsilon x 0 for z equal to 0, and the minus and plus z curvature. Okay, and the curvature is minus partial w partial x squared. Okay, so this is my nonlinear beam theory. I consider so that this is strength, okay, for this one, and this is this one. So the total strength will consider stretching and bending. Okay, yeah, bending. Right. Yeah, for the positive z positive, it will be the tension strength. If this z is negative in upper side, that will be compression strength. Okay. All right.